Another video clip I showed you was yet a bunch of people on a merry-go-round, and they have the merry-go-round spinning, and what they do is they purposely move their weight towards the inside. And what you see is that the merry-go-round instantaneously speeds up. So here's our system. Merry-go-round is a disc, right? And let's make its mass m, radius r. 1/2 mr squared is our moment of inertia for a disc. If we look at the people around it, you might have a person there, a person there, a person there, a person there. We're going to treat them as point masses. All right, they're little dots on the disc as far as I'm concerned here. So, moment of inertia of point mass, and we'll call these people little m. It'd be m r squared. Now I read a lowercase r because we don't know where they are. Initially they're at the edge. So for the initial conditions, what we're going to say is this. They have a moment of inertia of m times the radius of the merry-go-round squared. But then afterwards, this is before. Right after, they're going to move in. Now let's move them in halfway in so that this is just 1/2 r from the center. So then their moment of inertia, each of those point masses will change. It'd be m times 1/2 times r, square that. So we're going to get 1/4 mr squared for each of those point masses. Keep in mind there's 4 of them. So if we look at the initial conditions, the total moment of inertia is going to be that of the disk plus each point mass here. So before, keep in mind, let me label this as after. Before, you have an I value, a total I, of 1/2 mr squared. That's a capital M, plus 4 point masses that are lowercase m, and they're at the edge, so it's the radius squared again. And what we would end up getting is, I guess we would have 1/2 m plus 4 lowercase m in parentheses times r squared. All right, so there's the total moment of inertia for before. Afterwards, it's going to be different. They've moved in. The disk is still the disk, same radius, same mass, but the people are now much closer to the center. So you have 4 m 1/2 r, square that. All right, so each of those end up being a 1/4. So basically what will end up happening is that you get the disk being the same, but now you've got just a term of m there once you do all the math, and you have r squared there. So you can see, just comparing these terms, that the moment of inertia of the system has changed. Now, keep in mind, when you watch that video, nobody on the outside is allowed to touch the merry-go-round once they bring themselves inside. So the act of just leaning forward or even walking towards the center is going to end up speeding up the system because the angular momentum is conserved since there is no external torque. L1 is equal to L2, so what we would have is that I1 omega 1 is equal to I2 omega 2, and since I2 is less than I1, that must mean that omega 2 is greater than omega 1. And again, you would see an increase in kinetic energy. What you might notice in that video is that a few of the kids, I think they have difficulty actually bringing their mass inwards, just leaning forward, because they have to do positive work in order for that to happen. So, it's actually a very complicated process, but very easy to analyze when you do conservation of momentum.